In this video, we're going to talk about arithmetic and geometric progressions. So I can title it Progressions in general. And it's within the set of algebra videos using Maxima. We start with a worksheet where we provide definitions. And for example, when we talk about a series, it's just a succession of terms that may or may not have an order, but this actually has an order. This is the odd numbers, and every number, any subsequent number is obtained by adding 2 to the previous one. So that's the rule that defines this particular series. If we had this one, we'll notice that every term is obtained by multiplying the value of 2 to the previous result. So this is sort of an example of a arithmetic series when you add things, and this is an example of a geometric series when you multiply things. So in an arithmetic progression or arithmetic series, the first term I'm going to call A1 is a constant value that I call A. Second term is A plus a increment that I'm calling R. The third term will be the value A plus twice the increment, because all what we do is take the previous term A2 and add the increment. But A2 is already equal to A plus R, so this is equal to A plus 2R. In that way, we can get to the nth term, A sub n or an, and if we follow these rules, will be equal to A plus A minus 1 times R. So the n term is given by A sub n or an equal A plus n minus 1 R. Here's the progression, 4, 7, 10, determine the 15th term. All right, so the first term is the 4, and the increment will be the difference between 7 minus 4, which is 3, or 10 minus 7, which is 3. And so we are after the term number 15, and we have the expression that the n term is equal to A plus n minus 1 times R. And so it tells me that the 15th term in that sequence, in that progression, is equal to 46. By a similar token, we can calculate the 23rd term, that will be n equal to 23, for the first term being 4, and the increment being actually a negative increment, we can see here, equal to minus 5. So it turns out that the 23rd term for this progression will be minus 101. This is a decreasing progression in the sense that the terms start decreasing in value as we increase the position. Determine the 38th term in a arithmetic progression where the first term is equal to third, the second term is equal to 3/2, so the increment is going to be equal to 3/2 minus 2/3, and we're looking for the 38th term, so that term is going to be equal, the increment is equal to 5/6, and that term is equal to 63/2. Determine, for example, the 42nd term of this sequence. We have the first term equal to minus 2. The increment will be minus 7/5 minus minus 2, and we're looking for the 42nd term. That's the value of 113/5. If we know the first term, A will equal n, the n terms an equal n plus 1 plus r, we can find an expression with the first term, the increment r, or the position. I'm cleaning the values of an, r here, and then I'm solving for a here. The first term is going to be equal to 1 minus n times r plus an. The increment will be an minus a divided by a minus 1, and the number of terms will be equal to r plus an minus a over r. For example, the 15th term in arithmetic progression is 20, and the increment is 2/7. So 15, 20th to 7, find the first term is equal to 16. Find the increment of an arithmetic progression. So the first term is minus 3/4. We're talking about the 8th term, and that 8th term is equal to 25/8. So the increment will be 31/56. How many terms are there in an arithmetic progression? See, if the last term an is equal to minus 13/3, the first term is 2, and the second term is 5/3. If the second term is 5/3 and you subtract the first term, then you get the increment, and then you can use this formula to calculate the number of elements in that sequence, and it turns out to be 20. Generating an arithmetic progression using Maxima. We're going to use this function that's called makeList. When we present values like these in Maxima, they call a list. And so makeList will produce a list, and to produce the list we need to define the kth term as a plus k minus 1 times r from k equal from 1 to n. For example, if I have an initial value of 5, an increment of 2, and I want 10 elements in that list, I use the make list example right here, and then you get 3, 6, 9, 10, and there is an increment of 2 in within each one of those sequences. In an arithmetic progression, the sum of the two terms equidistant from the extremes is equal to the sum of the extremes. And so, for example, if you have a first term here, a, and then the second one is a plus r, and then there's this term a1, which is at a distance, a certain distance of the number of elements from a, and then you have this term a2, which is at the same distance from the last element an. It turned out that if you add this term plus this term, it's the same as adding the first term and the progression and the last one. This can be proven. For example, a1, if there are n prime terms between a1 and a, then you could write a1 equals to a plus n plus 1 plus n prime plus 1 times r, and then the n term, the last one, will be equal to a2 plus n prime plus 1 plus r. So if you add these two together, or subtract them actually, a1 minus an, will give you a minus a2, and then switch in terms, you get a1 plus a equal to an plus n, which is what we wanted to demonstrate. Check this fact with the p. Well, if we take 5 plus 23, that's the sum of the extreme values. And it's 7 with 21, 9 with 19, 11 with 17, 13 plus 15. They all add to 28. If the term and the number of terms is odd, like in this case when we have 7 terms only, we can check 5 plus 17, 7 plus 15, 9 plus 13, and then 11 is sort of left alone. But if we duplicate that, that will give you the number, the double number, the number of the sum of the two extremes. Basically, when you have an odd number of elements, then the middle number is added onto itself. Sum of an arithmetic progression. We're going to find a formula here. And it turns out, because the symmetric terms add to the sum of the first and the second term, and there is n over 2 sums, the sum is going to be equal to this quantity. For an odd number, for an even number, the same thing. So the general formula is this: the sum of the elements in a arithmetic progression is equal to the first term plus the last term times the number of terms divided by 2. For example, determine the sum of 12 first term of the progression 7, 13, and so on. So the first term is 7, the increment is 13 minus 7. The last term is going to be calculated this way, and the sum is calculated this way. Check by actually adding the terms of the progression. Well, first, we're going to do the make list for all the terms, and then we're going to use this command from Maxima that's going to apply to every term in P the plus sign. In other words, going to calculate the sum of all those terms equal to 480, which is precisely what we found over here. Determine the sum of the 13 terms of the arithmetic progression, fix 6, 1 over 12. So fix 6 is the first term, the increment is this, and 13, this is the last term, and this is the sum. There's a study, very likely, that Carl Friedrich Gauss, the famous mathematician, was in elementary school, and the teacher was distracted and asked the kids to add the numbers from 1 to 10 by hand. And so Gauss immediately solved the problem. And basically what he did is add the sum of a arithmetic progression. But the first term is 1, the increment is 1, and there are 100 terms. The last term is equal to 100. That sum is equal to 5050. The way that Gauss reasoned is similar to the way that we developed the summation formula here. The first number and the last number add up to 201. If I move up in 2 and down from 100, I get 101. And so you can see that you can pair the numbers up to the 50 plus 51, and there is 50 pairs of the number 101. So if you multiply 101 times 50, you get 5050, which is the result that the sum indicates in here. Interpolation. I'm going to clear the values of a, n, and so on. The increment is equal to an minus n minus 1. Now, if we know the first and the last term, we're going to interpolate m numbers in between. Basically, we end up with a sequence that has n plus 2 numbers, And so we replace n plus 2 here, and we end up with this equation to give us the increment. With that, then we can proceed to calculate the terms. For example, interpolate 4 terms in the progression that starts with 1 and ends with 3. We have a equal 1 and a equal 3, and we have 4 terms. Calculate r as 2/5, and n is just n plus 2. And then we can just make list of this generic term for k from 1 to n. And then we see that we have 1, 2, 3, 4 terms interpolated between 7 and 3. Interpolate 5 points between -2 and 5 plus 1/4. First term, last term, how many terms we have to interpolate. This is going to be the increment, and this is going to be the number of terms. And then we put that into a make list. The second and fourth terms on an arithmetic progression add to 22, and the third and seventh terms add to 34. What are those 4 terms? Let's clear these. And so we have the second term is a plus 2 minus 1, a fourth term is a plus 4 minus 1 times r, a 3 is a plus 3 minus 1 times r, the seventh is a plus 7 minus 1 times r. And then we have that a2 and a fourth add to 22, and then a3 and a7 add to 34. So wait, I need to define this values right here so I can add this together. Actually, let me start from here, and I'm going to clear a1 $, a2 apostrophe a2 $. I'm going to clear all of them so I can repeat this result. Doesn't seem to have cleared my A's. There it is. That's what I needed to find, and then you can write the equations like this. And I have an equation with 2 unknowns. If I actually subtract that from that one, I can get r equal to 12/4. And from this equation, I find a equal to 5. And those terms are 8, 14, 11, and 23.